So far we've talked about alcohol synthesis from alkyl halides, or haloalkanes. But there's another functional group that can be used as a precursor to an alcohol, and that's carbonyl compounds. So if we were to start, for example, with cyclohexanone, we could make that into cyclohexanol by reducing which in organic chemistry is often defined as either adding two hydrogens or removing an oxygen. In this case, we're adding two hydrogens. Both of these actually accompany gain of electrons which is the standard definition of reduction. But in organic chemistry, it's often more difficult to determine the oxidation number change on an individual carbon than it is to see whether or not you added hydrogens or lost oxygen. So in this case, we're talking about a reduction reaction being accomplished by addition of two hydrogens, one to the carbonyl carbon and one to the carbonyl oxygen. So the question is, what reagent might we use to add a pair of hydrogens across the pi bond of the carbonyl group? If you're like me, the first reagent that will come to mind that will allow you to add two hydrogens is hydrogen gas. Hydrogen gas contains nothing but two hydrogens. If we could figure out a way to break that hydrogen-hydrogen bond, which is very strong, approximately 104 kilocalories per mole, and then add one hydrogen to the carbonyl carbon and one hydrogen to the carbonyl oxygen, we could accomplish the goal. H2 gas is pretty inert. Usually, it takes a large activation energy to break that bond. So what we'll need is a catalyst of some sort that's going to facilitate the breaking of the hydrogen-hydrogen bond. Generally, we also run these reactions. These reactions are referred to as catalytic hydrogenation. At an increased pressure to lose Le Chatelier's principle, that the gaseous starting material will help us push the reaction forward. The catalysts that are used for this are generally members of the transition metal triad that contains nickel, palladium, and platinum. Nickel is generally used as a version called grainy nickel, which is produced by treatment of an aluminum nickel alloy with aqueous HCl. Aluminum reacts readily with acid to form aluminum 3 plus and H2 gas, whereas nickel reacts very slowly with acid and stays as the solvent. And if you wanted to balance this reaction, you would actually have to use 2 aluminum, 6 hydrogen as acid, forms 2 aluminum 3 plus and 3 molecules of H2 gas. So what you have, if you think of, and I'm drawing one that shows a regular repeating arrangement of aluminum and nickels. So this would be a 1-to-1 alloy. The aluminum nickel alloy doesn't have to be 1-to-1. What you're doing is you're dissolving out the aluminum. And then you've got holes where the aluminum used to be. Which is increasing the surface area. It creates what we call a spongy nickel. Thus increasing the surface area of nickel that's available to bind hydrogen. Palladium is generally used as the metal itself, but since palladium is expensive, as maybe 10% by mass palladium on carbon. So we have our carbon feed, and then around the outside of the carbon, we have a thin layer of the expensive palladium. Carbon black is cheap, palladium is expensive, so most of the volume is carbon, but most of the surface area is palladium. Again, the goal is to create a high surface area. And the most common platinum catalyst is platinum oxide, which is known as the Adams catalyst. Under the reaction conditions, generally at high pressure hydrogen gas and often an alcohol solvent, platinum oxide is converted into a very highly divided platinum metal. All of these reagents, grainy nickel, 10% palladium on carbon, and platinum oxide, or the Adams catalyst, are used to maximize the surface area of the metal that interacts with hydrogen. And hydrogen is absorbed very nicely into palladium or platinum. In fact, palladium is often used as a reservoir for hydrogen gas in fuel cells because it's much safer than having a reservoir of liquid hydrogen. Palladium will absorb a very large volume of hydrogen to form an interstitial billet. So we can use ready nickel, or 10% palladium on carbon, or platinum oxide, one of those catalysts. And we can use a high pressure of hydrogen gas at perhaps 30 to 50 atmospheres, and generally an alcohol solvent like methanol or ethanol. It's usually not necessary to heat this reaction, but the reaction might also be heated to increase the rate of reaction. The mechanism is occurring at the surface, and it's quite complex, and perhaps to this day not fully understood. But what is known is that in the presence of hydrogen gas, these various high surface area nickel triad metals will absorb the hydrogen into the cavities of the metal. So we have a metal surface, and on that surface there are some available hydrogen atoms. And then inside, to use platinum as an example, you've got some hydrogen atoms. So if we have a regular repeating lattice of platinum, I'm not sure if this is accurate because I'm not sure if platinum forms a face-centered cubic or body-centered cubic. I have to look that up. But there are some hydrogens in the small spaces separating the platinum. The hydrogens that matter are these that are on the surface. The pi bond likes to bond to the surface, so you will bond your carbonyl group into the d orbitals that are available on the metal surface, and then effectively a hydrogen radical will add itself to the carbon, forming a sigma bond between the oxygen and the corresponding surface. So we'll look something like this. Where we have our two R groups. In the case of cyclohexanone, both of the R groups are the ring. And then an additional hydrogen with its electron will bind to the oxygen and break that bond between the oxygen and the carbon, or the oxygen and the metal rather, to leave the metal surface with two fewer hydrogens on it and create your alcohol. So both of these hydrogens are added as hydrogen radicals. This catalytic hydrogenation reaction is not limited to polar carbon-oxygen bonds. This catalytic hydrogenation reaction also works on nonpolar carbon-carbon bonds, either carbon-carbon double bonds or carbon-carbon triple bonds to yield alkanes from the corresponding alkene or alkyne. And we'll see those in chapter 12, chapter 13 respectively, where we can use catalytic hydrogenation using hydrogen gas at high pressure with radionickel or 10% palladium on carbon or platinum oxide to reduce the carbon-carbon and carbon-pi bonds in the alkenes and the alkynes. Because this bond is polar, however, you can also approach the addition of those two hydrogens by using the dipole that has a significant partial positive on the carbonyl carbon and a significant partial negative on the carbonyl oxygen. So if we want to add hydrogen to the carbonyl carbon, we can think about doing it with a hydride ion. We effectively need H minus. And if we had H minus with a pair of electrons, it could readily attack the partially positive carbon and push that pi bond out onto the oxygen. So the question is, where do we get H minus? We know that we can get H minus from an alkali metal hydride. But we also know that those alkali metal hydrides are mostly ionic compounds, with the exception of lithium hydride, which is somewhat covalent because of the orbital size match between lithium and hydrogen, but the heavier alkali metal, sodium and potassium hydride, are effectively H minus. And H minus is a strong, very hard base. It's about as localized a negative charge as it's possible to get because of the small size of hydrogen. It's a strong, hard base. It's going to like to act as a Bronsted-Lowry base. And unfortunately for us, it's going to prefer to react with the hard acid, which is the hydrogen in the beta position, or sorry, the hydrogen in the alpha position, adjacent to the carbonyl, rather than the softer acid. So if we take sodium or potassium hydride and react it with cyclohexanone, the only reaction we're likely to get is an acid-base reaction to form hydrogen gas and the corresponding resonance stabilized ion referred to as an enolate ion. And you could calculate the equilibrium constant for that reaction if you knew the pKa of the alpha hydrogen which we do know is approximately 20 to 22, depending on whether you're working with an aldehyde or a ketone, and the pKa of hydrogen, which we know is equal to 38. So the equilibrium constant for this reaction is going to lie strongly to the right by the difference between the pKa of 38, the conjugate acid, and let's call it 22, the acid. So you would predict that this would have an equilibrium constant of approximately 1 times 10 to the 16th. The hard base prefers to react with the hard acid. The small proton is a much harder acid than the larger partial positive on the carbon. So that's a problem. If we want our hydride ion to react with the softer carbonyl carbon acid rather than just doing a deprotonation acid-base reaction to form hydrogen gas, we're going to have to do something to make it softer. So what can we bind it to that will make it softer? Well, we can't make it any bigger. Hydrogen is the size it is. But what we can do is decrease the degree to which it's an ionic bond and make it less partially negative or less completely negative by attaching it to something that provides a smaller electronegativity difference between the hydrogen and the metal or non-metal or semi-metal to which it's bonded. And two reagents that are very useful from that perspective are aluminum hydride, generally as the lithium salt, and borohydride, generally as the sodium salt. So LiAlH4 for lithium aluminum hydride. Which is sometimes abbreviated LAH, and NaBH4 for sodium borohydride. Are useful reagents for providing a partially negative hydrogen, because we know hydrogen is just a little bit more electronegative than boron. If you remember your electronegativities for boron, boron's about 2, and hydrogen is about 2.2, which means that there's a dipole that lies a little bit towards the hydrogen, but much less strongly than an alkali metal hydride, where the alkali metals have electronegativities that are on the order of 1. Right? Aluminum, if you remember, is somewhere around 1.6 for its electronegativity. Again, that's a much smaller electronegativity difference, larger for lithium aluminum hydride. And in fact, lithium aluminum hydride is much more reactive because of that than sodium borohydride. And that will be reflected in the rest of the reaction conditions for running this reaction. So what we've done is we've introduced a source of hydride that is much less ionic. Those significantly covalent bonds decrease the localization of the negative charge on hydrogen. So it acts like hydride, but it's not as basic as an alkali metal hydride. These can be readily made by taking the corresponding alkali metal hydride and reacting it with AlH3, which is called alane, or BH3, actually as B2H6, which is diborane, because BH3 itself is unstable, and sodium hydride plus B2H6 will generate sodium borohydride. Lithium hydride plus alane will generate lithium aluminum hydride. Both of these compounds are readily available. So we've decreased the basicity. We have an electron deficient group 3 element. The hydride ion simply donates in to fill the octet, leaving the lithium cation as the counter ion. Because of the reactivity of lithium aluminum hydride, we can't use a protic solvent, or we would simply get an acid-base reaction where the lithium aluminum hydride would depropane the protic solvent. So when we use lithium aluminum hydride, we need to do it in an inert solvent. Usually, that inert solvent is either diethyl ether or tetrahydrofuran, which is abbreviated THF, which is a cyclic ether. Ethers are inert. There's no acidic hydrogen to react with lithium hydride, and the product of that reaction will be the corresponding alkoxide, where we've added a hydride ion. And the mechanism simply looks like this, where the lithium aluminum hydride donates hydrogen with its pair of electrons and pushes its pair of electrons out onto oxygen, and the lithium cation goes along to the right. The hydrogen that's bound to the oxygen comes from the second step, which is reaction with aqueous acid by a simple acid-base reaction, where the hydronium ion donates a proton to the alkoxide ion to form the corresponding alcohol. And water. And the alkali metal cation. So it's a two-step reaction. Lithium aluminum hydride and ether converts the alkoxide, and then aqueous acid workup converts the alkoxide into the corresponding alcohol. It's different from catalytic hydrogenation because this hydrogen comes as H+, from the aqueous acid, whereas this hydrogen comes from H- from the lithium aluminum hydride, AlH4- ion. So we're adding H- to the carbonyl carbon and H+ to the carbonyl oxygen. This hydride reduction, carbon pi bonds, because the bond polarity is necessary for the partially negative hydrogen to react with the carbon in the first place. Sodium borohydride is significantly less reactive than is lithium aluminum hydride. So sodium borohydride can actually be used in a protic solvent in a single-step reaction, where the borohydride acts as the hydride source, and the solvent, often an alcohol like ethanol, but it can be water, acts as the source of H+. hydrogen to the carbonyl oxygen, the pi bond will break and pick up a hydrogen from the alcohol and push a pair of electrons on toward the alkoxide. So the reaction is simply NADH or in ethanol solvent, and it goes in a single step to produce the corresponding alcohol plus pH3 plus the sodium salt of the solvent, in this case sodium ethoxide. The ethoxide ion will now react with the borohydride to generate a species that is capable of donating a second hydride. Both lithium aluminum hydride and sodium borohydride contain 4 hydrogens, and therefore each is capable of reducing 4 equivalents of carbonyl compound to the corresponding alcohol. I've shown it with a secondary alcohol in this case. Ketones are converted into secondary alcohols, but primary alcohols can also be obtained through hydride reduction by using aldehydes as their starting material instead of ketones. The mechanisms are the same. The source of the hydride is still one of these tetrahedral group 3 hydrides, either borohydride or aluminum hydride. So we could, for example, convert pentanal into 1-pentanol by treating with sodium borohydride and ethanol in a single step, or by using lithium aluminum hydride in a 2-step reaction. Benzaldehyde and be treated with lithium aluminum hydride in ether, followed by an aqueous acid workup. To produce benzyl alcohol. Is the benzyl group. And it's abbreviated BN. So if you see that BN abbreviation, you'll know that it refers to a benzyl group, the phenyl group attached to a CH2 or phenylmethyl. So both of these hydride reducing agents can be used to make primary alcohols from aldehydes or secondary alcohols from ketones. Tertiary alcohols are not accessible by hydride reduction because in both cases, one of the hydrogens is coming from a hydride agent, and if a tertiary alcohol were present, there would be no hydrogens attached to the carbon-bearing alcohol. So if we're going to do tertiary alcohols, we have to come up with another method. Hydride reduction can only yield primary and secondary alcohols. And that's what we'll talk about in the next video, how to make tertiary alcohols from ketones, secondary alcohols from aldehydes, and primary alcohols from formaldehyde using organometallic